this seminar hosted by ISI as part of the Game Changer series. For those of you who follow this series online, this seminars happens once a month. We bring you the latest topic and the most engaging speakers. If you have questions for our speakers, please put them in the chat and we will just answer them at the end of the seminar. And it is our pleasure today to have with us distinguished Bloomberg professor David Singh from Johns Hopkins University. So David is a longtime colleague and friend. He started his career with a PhD at the University of Arizona. Then postdocs at the Lunar Planetary Lab in Arizona and the Institute of Astrophysics in Paris. In 2009, he moved to Exeter in the UK, where he stayed until 2018, then decided that he was ready to come back to the US and took a position at Johns Hopkins University. So David is a world-known expert of exoplanets, especially related to the physics and chemistry of their atmospheres. He has extensively used the Hubble Space Telescope. He has pioneered studies of atmospheres with Hubble. And now he's very excited about all the new data that he's getting from JWST. And today he will show us some very, very new results. So you have the floor, David.
All right. Thank you very much, Antonella, and thank you for the invite. Let me go ahead and share my screen. All right. You can see that? Okay. Yes, so it's my pleasure to talk to you today about exoplanet atmospheres and the spectroscopy in the era of JWST. And I like this lecture series, Game Changer, because definitely JWST has been an absolute game changer for exoplanet atmospheres. And I want to hopefully show you some of that today. Before we begin, I just want to give many thanks to a lot of the students and postdocs and some team members. I'll show primarily results that I've been involved in, and that includes undergrads and PhD students and postdocs, and then also like the NearSpec team, GTL team, the WASP-121 phase curve team, and what we call the no error team. So you can see the PIs here. So this has been a large effort. Also the ERS, transit ERS program that, many people involved in that. We have over 300 members. And of course, this very special thank you to everyone who made JWST happen over these last decades. And that's, of course, tens of thousands of people around the world. It's an amazing machine. And I can't wait every day, to look at new data because it is absolutely game changing. So when we talk about JWST being game-changing for exoplanets, going into it, what were some of our expectations? Well, I'll kind of lump these in kind of two categories. One, giant exoplanets. And for giant exoplanets, we've been studying these from Hubble and ground for a couple of decades now. So for JWST, we really want to see really new capabilities, and that giving new physical constraints and better precision, and also unique constraints, learning things we couldn't do before. And we want to definitely have new data on very long-standing exoplanet problems. Some of the, we really want to crack open how these giant planets work. And I'm arguing we're starting to be in an era of precision planetary science for giant exoplanets. So the sort of data you can go and talk to the solar system people and not be embarrassed about your error bars, basically. And asking some of the same sort of questions we're asking for solar system too. Not, of course, to the same level of detail, but we have many more planets to look at. And separately, it almost feels like a whole other field of rocky planets. And the expectation is JWST should be able to open up a new frontier on rocky planets. And when you start to talk about rocky planets, there's a whole lot of interest for life on these planets and biomarker signatures. And of course, we have a very long way to go. But with JWST, we are at the very start, at least for some categories of terrestrial planets, and those are, of course, the runs around M dwarfs. So small planets around small stars. So, so we hope to show you today some of the data for JWST kind of in these two kind of fields. So let me begin by talking about the science questions. And I kind of look at a lot of these questions sort of as a pyramid, and many people at the top of the pyramid want to know, are we alone? But there's a whole lot of more fundamental questions we need answers to that we just absolutely don't have. For instance, what is the diversity of planetary atmospheres across the galaxy? Even with giant planets, we actually have absolutely no idea still after several decades of looking at them. And we know even less about how the local physics and chemistry affects planetary atmospheres and how those change as a function of things like the stellar environment or how planets formed. So to answer this is where JWST becomes a really a game changer. It's going to build a solid foundation where we're going to actually look at a lot of these planets for the first time. And remember, these are planets we have basically no data for, very, very little data for giant planets, and even less so for terrestrial planets. Okay, so let's get everyone on the same page. I'm going to talk about transiting planets. JWST is also very good at directly imaged planets, but I won't get into that. So let's talk about how JWST uses the transit method to get exoplanet spectra and detailed constraints. So transiting planets, these are the ones where the planet passes in front of the star as viewed from the Earth. And we look at the flux over time as the planet passes in front. There's a little dip in the flux from the star. And from that dip, you can measure the radius. But you can go further because atoms and molecules will absorb high in the atmosphere at specific wavelengths and lead to a deeper transit depth, which we can measure. So the trick is to measure the planet radius at as many wavelengths as possible, and you build up what we call a transmission spectra. And you can think of this as an absorption spectra. So it's that special place, it's at the planetary limb, this place between the day and the night. And we're measuring radius directly, so we're measuring altitude. And typically, we're talking about pressures, about millibar is usually what we're sensitive to, millibar and lower pressures. On the flip side, if you wait for the planet to go behind the star, then what you can do is you can see the eclipse and measure the light from the star alone. And from that difference, you get the flux of the planet. So then you can measure the planetary flux directly. And especially in the infrared, that gives you, for instance, the black body temperature of the planet. So you can get the actual direct emission spectra. And this is much closer to the sort of spectroscopy people are used to in astrophysics, looking at stars and brown dwarfs and so forth. And this, of course, because we're looking at now the day side of the planet as it goes behind, you're looking at the whole integrated flux and typically pressures from sort of bar to millibar is what you're looking at. Or you could also look in the optical, and instead of the thermally emitted light, you can look at the reflected light of the planet. And so we've been doing these techniques for over a decade, and JWST is now really opening these up in a new way. And if you have a short period planet, you can actually look at this entire phase curve, what we call it. And here I've drawn a dotted line of the stellar flux, and all the sort of light above this will be light from the planet. So then if you watch the planet all the way around, you can get a map of the planet, and you can do this as a function of wavelength too, and look at phase curve as spectroscopy. And this is one of the harder measurements to do, and you really need a very stable telescope to do it. And this is where JWST can really shine. So I'll show some phase curve spectra in this talk. But, when you're talking about new methods and new techniques, here's a couple of new ones that JWST is really opening up. And one is eclipse mapping spectroscopy. So when the planet goes behind, you can think of it as kind of taking small slices during the eclipse, and you can actually back out the brightness of each of these slices during ingress and egress, and sort of map the full day side. You can get slices going one way and slices going the other way, and you actually build up a 2D map of the planet. And you can kind of do something similar in transit, because when the planet is in ingress or egress, you're actually sensitive to just one half of the planetary limb, and you can actually extract the spectra from one limb to the other and differentiate these. So this is what I call sunset sunrise spectroscopy. So now we're looking at really all aspects of the planet, and we can get a very detailed look all the way around the planet, throughout the atmosphere, really three-dimensional look, multi-wavelength look at the planet. So this is, absolutely groundbreaking with JWST. All right, so here's the exoplanet landscape as of my birthday last year. So we have over 5,000 planets detected. Where can we get spectra with JWST? I sort of just roughly highlighted these in green. Transits, we're looking at close-in planets, and imaging you could also do for the planets very far from their host stars. So already you can see with transits, JWST is capable of looking over a broad range of planets, all the way from gas giants down to terrestrial planets. And one thing to keep in mind, because this is such a large range in planet sizes, it turns into a large range in the sort of quality of a spectra that we get from information rich for gas giant planets, where we're starting to ask very detailed questions about the broad physics and chemistry and how the planets form, to sort of down here at the terrestrial planet regime, where that's really the frontiers, and we just want to know very basic questions. Does the planet have an atmosphere or not? Can we see it? So keep that in mind as we're, exoplanets is now a very large, diverse field. So let me go at first, just kind of set up some of these detailed questions we're asking for giant planets. So this will come into play when I show you some of the data later. So we want to know how planets form, giant planets form. And we have a pretty good theory, which is the core accretion model. So just very quickly, planets form in a protoplanetary disk, and they, going from all the way from dust over some millions of years, until core accretion model says roughly at about 10 Earth masses, and that sort of planetary core will be large enough to then start to pull all the gas around it. And then that is a runaway effect, because it pulls some of the gas and it gets heavier, and so then it can pull more gas around it and then grow to very quickly to a gas giant planet. And things like the Earth didn't quite make it up to that level, that mass. So there's this prediction of a runaway gas accretion roughly at 10 Earth masses. And from this core accretion model, we have also, a detailed, predictions for the mass metallicity. Here's the metallicity versus the mass of the planet. So you see the solar system follows a very tight trend here. And here you can see the first exoplanets, where we start to put on this plot too. And this is thought of as a direct consequence of the core accretion theory, because as you build up more gas on your planet, it looks more and more like the disk and the star. So hopefully we can see this as for exoplanets too. And this is where JWST comes in. We're really going to start to get precise exoplanet metallicities, and also more. So we should be able to start to test some of these core accretion theories. And already there's some real head scratchers. I'll show WASP-107 a bit later. This is a very, very puffy Neptune mass planet. And if you look in the literature, there's estimates for the core mass actually, and it's actually less, they have less than 4.6 Earth masses. So it's not clear how a planet like WASP-107 could have a runaway greenhouse, or runaway gas accretion with a core this light. So this is a real challenge to core accretion theory. And I'll go through one other kind of rich science questions we're looking at, and this is the atmospheric chemistry. So quickly, if you just assume equilibrium chemistry, and that's basically where most people start. Here I have the pressure versus temperature and the TP profile for a planet. You'll find planets over here in the hotter regime should be very CO rich, and very cold planets over colder planets over here should be very methane rich. So this is a very basic prediction that we've had for the last several decades. And actually, if you start to look at a lot of the hot Jupiters we've had from Hubble and so forth, they basically more or less are consistent with this picture. We've been able to look at sort of hot planets. So here's 10 planets from 1,000 to 2,000 Kelvin. And you see water vapor in here, which is predicted from equilibrium chemistry. And also carbon dioxide has been seen too. But with Hubble, you're not really sensitive to this equilibrium chemistry. So here JWST comes in as a game changer. It's going to open it up to much cooler planets. So that's great. And especially as cooler planets, we have to start to worry about disequilibrium chemistry. So vertical mixing from the deeper interior. We actually have no idea how strong vertical mixing is in these planets. The typical eddy diffusion coefficients we use, we have no idea what they are till about 8 orders of magnitude, which is kind of unbelievable. But you could have mixing from the deep atmosphere near equilibrium conditions to the top of the atmosphere. And this could be sensitive to things like the interior temperature. So here's TP profiles with hot interiors and cold interiors. You can imagine mixing from either CH4 poor regions or CH4 rich regions for colder interiors. But of course, these are three-dimensional objects too. So winds blow from the day to the night side, mixing horizontally, and also photochemistry is important to XUV light. So we have all of these complex chemical processes going on. We don't know which ones are dominant. Is it vertical, horizontal photochemistry? How does are these interiors hot or cold? It's hard to say. So JWST should give us some great constraints with carbon and oxygen chemistry. All right, so we talk about just some science with terrestrial planets. We're really looking at the frontiers because we basically have almost no data at all. So what we really want to know right now is just, do some of these planets, terrestrial planets, have atmospheres at all? And it's not an easy question because we can look at M dwarfs because they're small and we get large enough signals to potentially get a spectra out, but these have very strong XUV irradiation. So a lot of these planets receive 100 to 1,000 times the XUV illumination as our own dirt does. So it's not quite clear, can you have even a secondary atmosphere, or will even that get blown off and we have a lot of bare rocks, and what the landscape is. So there's this idea of the cosmic shoreline. If you plot planet escape velocity versus things like equilibrium temperature or even the XUV with the host star, where it's hotter and lighter or less massive planets, they probably don't have atmospheres. And over the other side, for lower temperatures and higher surface gravities, it's easier to hold on to atmospheres. And this is borne out in the solar system, and we want to test this if sort of this happens, and with M dwarfs on terrestrial planets too. So I just kind of show here kind of like a guess where you might find atmospheres or not, but we have actually no idea where this line would go, or if any of these M dwarf planets have atmospheres. So this is where JWST is going to be a game changer. Hopefully we're going to get a yes or no answer on this question. Before I show some of the JWST data, here's a quick sneak peek of where it's headed. This is sort of the last couple of decades with Hubble. Here now is 25 planets, giant planets anyway. And what we're seeing is giant planets are extremely diverse, much more than brown dwarfs. And so what we really need is a very large number of high signal noise spectra. So hundreds of planets, even giant planets, are going to need hundreds to start to uncover trends and learn how these go. All right, so let's get into it. Let's look at some data. So we're now a year and a half in for JWST. So let's start and let's see some of these new capabilities. So I was lucky enough to be involved in the commissioning on NearSpec, and thank goodness they decided to like, hey, let's calibrate the TSO modes for exoplanets because we know this is going to be so important. So a transit of HAT-14 was taken during commissioning, and this was intentionally a high gravity planet. This is a 3 Jupiter mass planet, and the 3 Jupiter masses means the atmospheric scale height is very, very small, and you basically should get a flat line. So that means we should be able to test, basically calibrate the instruments and see how well they perform. Well, here we have what the basically almost raw, right out of the box photometry was for NearSpec. And when I saw this, you couldn't really share anything at the time, but I remember just thinking to myself, my entire field just changed overnight, and it's going to be completely different throughout the rest of my career. I was just so excited to see this, and this, first data set is sub 100 ppm signals. And, I struggled for my whole career trying to get precision out of instruments that just weren't designed for it. And we've all struggled to try to get to these small sort of ppm level signals. So, and the real game changer is the unbelievable stability of JWST. Thank goodness the faint galaxy people wanted their galaxy to be on the same part of the pixel for long periods of time. That basically unlocks really unbelievable photometric quality. So that's the real game changer here. And here's a shout out to some of the undergrads I'm working with here at Hopkins. We've been re-releasing this HAT-14 data with the latest methods, a year and a half later. And even though this is a high gravity planet and that it ranks 805th best that you would want to look at for like signal sizes, you can actually still get atmospheric constraints. So this is real proof that JWST can actually get constrained to 4,000 planets, more than 1,000 planets, which is amazing. So this is what I'm looking forward to over the next couple decades, knock on wood. So I just want to go through a little bit of, almost starting at the beginning. So that was during commissioning, and the first data that the community got was from the ERS program, which is a great program. Our transit ERS program has been a great experiment in open community science. This is PIs, Natalie Patala, Kevin Stevenson, and Jacob Bean, but there's over 300 participants worldwide. It's been a very long effort, over 8 years. So we've hosted community data workshops and challenges to really prepare the community for using JWST. And there's 3 main programs here. I won't get into all the results. There's a phase curve program. The phase curve is just out today on arXiv. Please take a look at that. Also, there's we wanted to test the bright star. How bright can JWST go? So there's a HAT-18 SOS eclipse. And also, we wanted to test all the near infrared modes and compare them. So that's what we did with WASP-39. Why did we pick WASP-39? Well, several reasons, but one, it's feature rich. So we wanted to have actual features to give to our modelers and challenge them with. And WASP-39 is kind of special because it's potentially high metallicity. High metallicity means there should be quite a bit of carbon dioxide. So CO2 is a molecule we've never seen before. JWST, that should show up immediately. So here's the different modes that we looked at it. And the first data set was released, with the commissioning. So we had this right away. So here is the work we did with Hubble, showing the STIS and the wide field camera spectra. You can see nice water features. So here's the prediction from out in Spitzer. We should see CO2. And here I'll show just the raw data that we got 24 hours after the release, and boom, there it was, the CO2 feature just as predicted with from the previous data. So this was a great moment. I'll never forget just being able to see a new molecule, such an important molecule, carbon dioxide, and just popping right out. You can see in the photo, here's grad students so far, and just, there's CO2, there's a new molecule. We really can do chemistry with these exoplanets. Here's the full spectrum from the prism. We see the CO2 feature. We see lots of water. You see sodium. Here's a nice big broad wavelength with smaller bars. It's pretty amazing. In preparation for this, we had thousands and thousands of models run. We actually had a new bump here that we noticed in the data right away. And this was not in anyone's forward models. And this was very exciting times. But wow, what is this? What's this new molecule? So I just wanted to quickly go over, how do you identify a new molecule with JWST data? So one, you want to rule out as many possibilities as you can. So here is in the ERS paper, all of the different molecules we ruled out, trying to figure out what this little bump was. We also searched the literature for possible non-equilibrium sources. And so sulfur photochemistry was predicted by Kevin Zomley in 2009. We also want to confirm your feature is real, because this is a little bump. You don't know if it could be systematic. So we also have the G395H data, which sees the bump too. And you want to verify this with other wavelengths. So there's a large feature in the infrared with MIRI. So that data we got, and that's coming soon. And that definitely confirms this as SO2. So please, when you have a new little bump in your data, what not to do, see a little bump, and then just say, oh, look, I found life on a planet. So, it's best to be a bit more thorough. And why was this so exciting? Because that little bump was SO2. And this was the beginning of, photochemistry and chemistry in exoplanets. So this is the first detection of exoplanet photochemistry. Basically, water breaks up and goes through this big chain reaction to finally get sulfur dioxide. So we can actually do exoplanet photochemistry with these spectra. So I don't have time to go over all of the results, but there's going to be a large set of 13 papers in Nature. Many of them are out. Again, the phase curve paper is out as of today, so go look on the archive for that. Some great results, and more is coming. So this was, this is basically still from like day one, but there was also released at the time the early release observations as well. So one of those data sets was HAT-18, and HAT-18 was very interesting because it's also a bit cooler than a lot of the planets that I've showed before. So this is sort of in the cool, warm regime, and cool enough to where you do start to expect methane in the atmosphere. So methane has long been missing in all of our data that we've been seeing of pre-JWST. So this, and also the first data sets seen from JWST, methane has also been missing. So WASP-39 and WASP-43. And when here Guanwei Fu here at Hopkins analyzed this data, early published it right away as well. And here the green is the prediction how much methane we should see. There's a feature that shows up at about 2.4 or so microns, but we don't see that at all in the data. So in fact, we only get limits for how much methane there is. And so so then the question, like, okay, there's no methane, there's some sort of disequilibrium process happening, and what is it? Is it the photochemistry like we just saw with WASP-39? So basically, maybe the XUV radiation is breaking up the CH4, or maybe there's mixing from below, so mixing from the deep hot atmosphere and getting rid of it as well. So we can't quite tell with this data set. We really do want to nail down how much methane is missing, which we'll need other data sets for. So there's this big mystery with the methane. And this gets me to WASP-107. And WASP-107 is a very special planet. It's very puffy, which means the scale height is large, and it's around a bright star, so you get very large signals. So all the GTO teams added WASP-107. The temperature is only 750 Kelvin, the equilibrium temperature, so it's very low. We should see very large methane features, but we actually already know from Hubble that the methane is depleted from Hubble, and actually just a bit ago, the first JWST MIRI spectra is out as well. And in that spectra, you see the SO2, which is exciting because photochemistry is now going on in this planet as well. But surprisingly, they saw silicate clouds, which you don't really expect at these colder temperatures. But that's a sign of potential mixing from the deeper, hotter atmosphere, perhaps. And the methane is meshing too. There's stronger features in the near infrared here than there is on Hubble, but they still only get upper limits. So this brings me to some of the data I've been working on lately, and this is part of the GTO team for NearSpec. So the PI here is Stefan Bergman. So here in NearSpec is if the planet was near equilibrium, here's the very large methane feature we should see. I mean, the spectra should be absolutely dominated by CH4, and we should see large CO2 feature as well. So here is the transit data for NRS1 and 2. It's absolutely glorious data, 100 ppm precisions, which bend down to about 10 ppm or better. And this is like one of the best transmission spectrometrics. So, we could expect very good signal to noise. So I'll go ahead and share the spectra with you. This is work that's under review now. So here's the spectra that we got. So right away pops out the CO2 feature, like you were expecting. There's SO2 here as well, which matches with what we see, what's been seen with MIRI. And well, we don't see a massive CH4 feature, but you do see this little peak right here. So you do see a little bit of methane. So that's very exciting. And there's water as well. So this is great because when you see methane, but it's depleted, now you can get some very firm constraints on the non-equilibrium chemistry. And for instance, we know now that the methane is depleted, the abundance is depleted by a factor of about 1,000. So it's really depleted compared to what it should be. So this is great. Let's model it. So here I've run some 1D atmospheric models that include vertical mixing and photochemistry, because remember, we don't quite know yet if the CH4 was destroyed by photochemistry or if you really need the vertical mixing from a hot interior to do it. So here, these error bars are the abundance constraints you get when you run a retrieval on the spectra. And then the dotted dashed lines are the equilibrium prediction. So here's the methane. It should be like 1 part per million or so. And then here is the data, sort of like at a ppm level for methane. And if you run the non-equilibrium chemistry, you can fit the data very well if you have a very hot interior. So intrinsic temperatures of about 450 Kelvin, which is much hotter than anticipated. And mixing, and you actually need very strong mixing. So KZZs, eddy diffusion coefficients about 10 to the 11 centimeter square per second, which is very large, very vigorous vertical mixing to mix the methane here from the deep atmosphere and sort of lock it into place, sort of at the millibar pressures that we see. Because we're modeling the photochemistry at the same time, here's the SO2. We can model the SO2 very well at the same time. And here's the methane getting depleted from photochemistry, but that doesn't really affect our spectra at all. So we really know that, one, the mechanism for this is the vertical mixing and not the photochemistry. And we have a hot interior. But we can actually go even further. We have very precise abundance constraints, and this actual interior temperature is really important too. And if you run interior structure models, we get a new core mass constraint for the planet as well, because we know the mass of the planet, we know the radius, we know how much heat there is in the interior, and we can constrain the mass of the core to about 12 Earth masses, plus or minus about 3. So this is, I think, the first time the core mass has been constrained in an exoplanet. And this is quite different than the previous upper limits before. You know, these constraints agree very well with the core accretion model. So I don't think we have to throw out the core accretion model or do anything quite drastic with it. So JWST game changer. These planets probably have very strong vertical mixing, which really changes the chemistry of potentially everything we're seeing. You know, on planets like WASP-107, we're sensitive to the deeper interior temperatures, which is great, and we're going to be able to get even constraints on the core mass of many of these planets, which is really exciting when you think about planet formation. All right, let's go from a kind of a cooler end to a hotter end. Let's go, we'll talk about another one of my favorite planets, WASP-121b. This is an ultra hot planet, and just the signal sizes are just so large, you get really ultra constraints for this. So this planet, ultra hot exoplanet, it's about 2,700 degrees Kelvin, which means on the day side, you don't really expect anything to be condensed out. You're basically seeing everything in gaseous and atomic state, which means all of the different atoms, molecules in the atmosphere are really accessible. Here's one of the early results from Hubble we were involved in. This was the first planet to really resolve the feature in emission. So in this case, you see water features in emission, and you only get that with a stratosphere, a hot gas on top of cold gas to put these features in emission. So and we get this inverted temperature pressure profile, and there's been a lot of interest over the last decades understanding how these stratospheres can work in hot and ultra hot exoplanets. So we want to look at this with JWST as well. So Tom and Michael Evans has a phase curve program here. I'll show you some of the first data that we published on this last year. So this is a phase curve with G395H near spec. There's a 37.8 hour phase curve. So you see it starts, you have an eclipse, and it goes through the transit, and it ends after another eclipse. And this way you get a nice baseline for what the star is at the beginning and the end. And you can start to look at the night side emission as well. And talk about game changer. This is a 37.5 hour stare. And here is the jitter of the telescope in X and Y. And you're talking about, the big telescope basically pointed at the same, hundredth or thousandth of a pixel for, day and a half. We've never seen anything like this. It's amazing. And the photometric quality you get out is just, it's basically perfect. It's amazing. So we're going to get a nice size spectra out of this. This planet has a huge day-night contrast. So the day side is about 2,700 Kelvin. We see that from the data. And the night side is about, just over 1,000 Kelvin. So these are two really different chemical regimes on the same planet, just day side to night side. So these are some results in preparation. Hopefully we aim to submit this pretty soon. Here is the spectra from the eclipse. And so you see these features also in emission in near spec. So carbon dioxide and water here. So the inversion that we saw with HST is definitely confirmed. There's a lot of CO in the spectra. So lots of CO in emission. This is a very carbon-rich planet. We're going to be able to study the dissociation. So this is a lot smaller. This water feature is smaller than what you expect because of dissociation. So here is showing the abundance constraints we get. So it's just so hot, and the inversion is so strong that water starts to break up. When you're getting at temperatures of 3,000 Kelvin or so. So here's the dissociation. So we're going to be able to study that in detail. Carbon dioxide doesn't really care. It's such a strong molecule. It can hold together. So the inversion is going to be very well constrained. We're going to really be able to look at that all the way around the planet and get exquisite C/O ratio constraints and metallicities. Although I'll save those actual numbers for when the paper comes out. So JWST game changer, definitely precision temperature pressure profiles all the way around the planet and abundance constraints as well. So here's some work I've been working on WASP 2021, this one, same data set. If you think, we have data of the planet going all the way around the star, we should actually be able to see the RV signal of the planet. And this isn't really something people have been talking about yet, but the planet is moving at about several hundred kilometers per second. So it should move a few pixels across the detector during the phase curve. And we actually get the full orbit of the planet this way. And so we can get a Keplerian measurement of the stellar mass because you actually measure the planet radial velocity, and then you can measure, you also have the radial velocity from the star as well. So now we can get a full double line spectroscopic binary. We get the very precise stellar mass from this. So here is the cross correlation. You can see the signal of the planet moving, and you basically get the right answer about 215 or so kilometers per second radial velocity amplitude, and this turns into very precise stellar constraints. So here's an example of like unprecedented constraints for the host star, the mass and the radius and the temperature. So here you see the distribution. And this is something that a grad student Zafar Rustam Kulov has been working on, is using the stellar density that you get from JWST transit measurements to really pin down the age. So you see how this works here. If you do the normal constraints with the stellar photometry and Gaia parallax, the stellar density changes the function of age, but it's not very well constrained with just those measurements. But if you fold in the JWST stellar density, it really pins down the age. So we know this WASP 2021 host star to about, just about 100 million years age, which is amazing. So stellar density is going to be the key. So watch out for that in the future, a paper on that. But you can even go even a bit further. This data set could possibly probe winds, and this could be very complementary to ground-based high-resolution work, which has been ongoing as well. And there's some results out in the literature about that. Because you can imagine there's velocity differences in the RV signal from several sources, such as a day-night asymmetry. The planet is a lot brighter on the day side than the night side, and so most of your flux is coming from the day side. So that gives an asymmetry. It's about 6 kilometers per second, but also the planet's rotating and the winds are rotating. So that will change just what you expect the signal to be as well by a few kilometers per second. And we're almost able to measure this too. So JWST game changer, we're getting precision masses from all the phase curves that we do for these hot exoplanets, and maybe even probe winds as well. So in the last few minutes here, I just wanted to share some results kind of from the new frontier. So now let's talk about rocky planets and the search for atmospheres. So this is from the NOAIR program led by Kevin Stevenson and Jacob Lustig-Jaeger. Here's the first result we had from that program, LHS 475. And here's the transmission spectra that you get. Of course, we're in a completely different regime than the very high signal to noise, like CO2 features that we saw. Here's a model for this terrestrial planet of a CO2 only atmosphere. And here's a methane model as well. And what we get is the spectrum is pretty flat. you don't really see too much CO2, but you actually get fairly reasonable constraints from this data set. It's kind of nice. There is no sign of stellar activity changing the transit depths. And here's kind of an illustration of some of the constraints you can get from the spectra. And basically thick CO2 atmospheres are kind of likely excluded. So like a clear Venus type scenario here is excluded at roughly like 2.5 sigma or so. So it's there's not quite apparent, like there's not very large CO2 signals that we've seen, but it's consistent with either a thin high cloud or a very thin Mars-like atmosphere, or even a bare rock planet. So this was one of the first results on, there's going to be a number of these sort of planets out there, and I'll show just some results from the others from the NOAA program. GJ46, 341, and 1132. There's no real strong signs of features yet. But unfortunately for some of these planets, stellar contamination is a real issue. So all these M dwarfs, many of them are quite active. And here on GJ46, you see that activity means that the stellar spots on M dwarfs can have water vapor in them. So that changes, and that can then basically fool your transit depth into thinking you have water on the planet when it's really water changing in the stellar spots. And so here's a model of unocculted stellar spots sort of here in orange, and a model with a water-rich atmosphere here in blue. And so you really can't distinguish with just this data set. We really need shorter wavelengths to really distinguish between these two scenarios. So, and then other planets like 1132, the spectra seems to change a little bit from one visit to the other, possibly because this activity is changing. So here you see kind of that same bump here on one and not the other. So, so there's no sign in any of these of like a CO2 atmosphere yet, but there's a lot of interest now in eclipses. Maybe the eclipses aren't as sensitive to the stellar activity. So maybe in some of these eclipse spectra or photometry coming up, we'll see something. So with that, let me just kind of say JWST was definitely worth the wait. It's the absolute game changer for exoplanets. We're going to get a lot of great results, for this area precision planetary science, new capabilities, absolutely, new physical constraints. It's like yeses across the board. It's absolutely game changing for atmospheric science and formation, like I was showing. And I think going forward, atmospheric vertical mixing is going to be strong and a very important effect. And I'm pretty excited about the possibility to look at many constraints on the core mass for a lot of these sort of planets. And as far as the frontier for rocky planets, JWST absolutely has opened up this new frontier, and just the photometric quality that we're getting really means this is actually possible. Stellar activity is a big pain, and are there secondary atmospheres? Well, we don't know yet. So we'll see. So this JWST has been a long wait, several decades. So it's actually kind of fun to think about the next future flagship mission, Hubble World's Observatory. So all those young PhDs and people out there looking forward to sort of like actual spectral Earth 2.0 planets. The JWST was worth the wait. I'm sure Hubble World will be worth the wait too. So thank you very much. So I'll stop here and we can take questions.
Thank you, David. This was fascinating, really, really interesting. I can still remember a long time ago when people were wondering whether JWST was going to be able to do exoplanet science. And here it is. And it's just 1 year after launch, so really amazing. So we have time for a few questions in the chat, so I will read them.
Okay.
and David will answer. So we have a question from Nuno Pereira asking, the JWST results of the atmosphere measurement of some planets in the TRAPPIST system are taking too long to be released. Was there some biomarker detected and researchers are making sure that they got the right answer before announcing a groundbreaking discovery?
Yeah, I mean, that's a good point. Like, wait a minute, JWST took some measurements of TRAPPIST very early on, even like a few months after data started to be released, and you haven't seen too much. So I showed a little bit, like there's some 15 micron spectroscopy out for a couple of the planets, and there is now some spectra available too in the literature, which I didn't show in the talk. But the reason isn't really a biomarker detect. The reason is the stellar activity in TRAPPIST is really strong. And so when you get multiple transits, you see spectra that change by a lot, even like a few days later. And that's just from the stellar activity changing by a lot. So that has turned out to be a really, really big challenge to model and actually do that correctly. So unfortunately, because the stellar activity is so strong, people really have to, hone in those models to get some sort of atmospheric constraints, and that's what's taken a long time to do.
Thank you. So there are a couple of questions about the recording. So as I said at the beginning, this talk is recorded. It will be posted on the EC channel on YouTube in a few days. So just keep monitoring our website, www.ecburn.ch, and it will appear in the next few days. Now we have a question from Roger Clark asking, why SO2 as photochemistry and not another explanation like volcano emission, like we see on Jupiter's moon Io, and many terrestrial volcanoes emit SO2?
Yeah, so on hot Jupiters, well, one, there's no volcanoes from the actual gas giant planet itself. And we don't really expect any moons like Io around them either, just because they're so close to their host star. It can be really challenging to hold on to a moon. So, uh, so so you don't really expect sort of like SO2 spewing from an Io-like moon around the planet, and then kind of polluting around. And also just, basic photochemistry predicts sulfur photochemistry and SO2. So that was predicted by Kevin Zomley in 2009. There's a number of other species as well that's just readily predicted when you do photochemical models.
Thank you. We have a question from Keith Thorne asking if you can detect winds or jet streams.
So with the RV, maybe, but I would say more from the actual spectroscopic eclipse mapping. There won't be a direct measurement like you could do in high resolution. So high resolution from the ground, you could actually see the lines shift and get a velocity from that directly. That's going to be a lot harder for JWST. So it's going to be probably more indirect, where you'll see hot spots shifted by a certain amount. And then the day-night contrast, and you'll be able to put limits on basically how fast the winds could be because of that. And the key to unlocking that will be very precise abundances, so you'll know precisely what the abundances and what the atmospheric constituents are. So that will help a lot.
Okay, thank you. So another related question, there will be soon weather forecast for exoplanets?
Weather forecast. Well, we haven't really actually seen weather on a exoplanet yet. That meaning like you see the planet change one epoch to the other. JWST could do it. So I mean, it's a possibility. And if JWST starts to see some variability in planets. They do see variability in brown dwarfs, for instance, and I know people are interested in things like weather on these gas giants. Then you could definitely get predictions like, hey, this gas giant over here should have very strong weather. It should look like this, and maybe the JWST could see it. So it's definitely a possibility.
So stay tuned. Another question asks, M-star activity leads to stellar winds. Beyond XUV, what role does that have in terrestrial planets' atmospheres?
The stellar winds, I suppose.
Yeah.
That's a good question. And this is probably where, there's a lot of speculation and a lot of things we just don't know yet. For instance, we don't really know about the planetary magnetic fields. It's completely unconstrained. And so without kind of that information, that will change the game a lot, whether these sort of terrestrial planets have strong magnetic fields or not. So so that could play a large role in determining how important the stellar winds would be on these planets.
Okay, we have a question from Daniel Angerhausen saying, can you elaborate a bit more about the stellar contamination? This is not surprising. There was literature about it, the method strategy for mitigation laid out before JWST. Is it missing simultaneous stellar characterization, or are the theoretical frameworks not robust enough?
Indeed, it's not surprising for people who've been paying attention. So yeah, thank you, Daniel. I would say the simple models that people have used just haven't quite been good enough. And they just didn't have enough auxiliary data with what so the data they have to really place firm constraints on there. So I think it's just a matter of the models you have aren't constrained enough. You need to know, have some other activity indicators or broader wavelength. And I think people were kind of surprised just how fast the stellar activity signal changes on TRAPPIST. So data from one epoch, even a few days later, the star seems to be quite different. And that, I think, took people off guard because no one quite expected that to happen at the level that we've seen it.
Thank you. So does JWST have the capabilities to measure star-planet interactions that affect planet magnetospheres, like aurora emission?
Usually when you think of aurora, you think of the ultraviolet, and that would be more of HST and Hubble's regime. But I mean, maybe there's some sort of line in the infrared too that could trace it. So possibly. I haven't thought too deeply about that though. Interesting question.
Thank you. Well, we have a long number of questions. This is extremely lively and interesting chat, which is really wonderful. So there is a question from Hugh Patrick Osborne. Nice talk, David. I was wondering if you would expect the strong vertical mixing you see also to apply to Neptune-like planets, or is there something special about giant planets under high insolation?
Oh, like if we're thinking about actual Neptune-like planets at very, at 20, 30 AU and or large orbital distances, maybe, but probably, I think the high intrinsic temperatures and the hot interior is really kind of driving it. That's my guess so far. So I think there's probably something more special about the gas or about the giant planets under these high insolation. But I should definitely think more about how that connects with the actual solar system too.
Okay. So finally, we have a question regarding horizontal mixing here. How well do we understand the effect of horizontal mixing in the case of methane depletion?
Well, that's a good question. So with the horizontal mixing, we're talking about gas mix from, like, say, the night side to the day side. And and you can look at the chemical timescales of that happening, and we can model it fairly well because we have general circulation models, and they can do that pretty well. The thing that the GCMs don't really have is they're not really good predictor for what KZZ and the diffusion coefficients are, because of they don't really things like the turbulent diffusion in those models is kind of a parameter that no one really knows what to dial to. And so the wind strength and stuff are something that they're going to have constraints from the observations. So, but hopefully with things like JWST, you can start to put some constraints on these things, and then things like the day-night mixing and the horizontal mixing should be, we should be able to model that fairly straightforward, knock on wood, with the GCM models. It will be much harder to fold in the vertical mixing with that, just because the timescales are so much different. And that's a hard thing to measure or model with the GCMs.
Fantastic. Well, I think we can call it a wrap now, and thank our speaker again for this fantastic talk, which generated so much interest. Thank you, David, really. And to everybody online, thank you for following us. Stay tuned for the recording that will appear very soon on our YouTube channel. And take a look at the next Game Changer seminar. We're offering always the next Game Changer results for you to enjoy. So thanks, everybody. And thanks, David, again.
Thank you.